Wrong hand. Hello. Welcome back. How you doing? Hopefully everyone's all right out there. I had to venture out this morning, go to the grocery store. Every morning the local Payless has the 8 to 9 a.m. Geezer Power Hour, for the older folks and those who are immunocompromised. As a largely in remission asthmatic, I suppose I could take advantage of that, but I decided not to. But I have learned that if you don't want your dinner to be an adventure, you had better get there first thing after all the old people leave, because stuff goes fast. I mean, if you get there first thing in the morning, you can more or less get the things you would normally get. Although, like, the fresh fish and meat counter is, like, half gone. But if you get there at 1 in the afternoon, you're just like, I think we'll have, cheddar bratwurst. That's what we're going to have for the next 6 days. So, you got to stay on top of it. Okay, so, last time we were talking about the limit of a function as x approaches a cluster point of the domain of the function. We had done a few examples. So we had done the basic example with the constant function, and we had done the example with the identity function, and then we did a slightly more complicated example with the function x squared. So the next example that we're going to take care of is the following. So let's let c be bigger than 0, and then what we're going to do is show that the limit as x approaches c of 1 over x is equal to 1 over c. Okay? And similar to the question of the limit as x approaches c of the function x squared, there's going to be a little extra work here. There's going to be a sort of first stab at delta, and then a second stab at delta, and taken together, the minimum of these two deltas will do the trick. But it's also going to bring up something which was part of a question on Piazza. So after I do this example, I'll try and explain how that relates to the question on Piazza and therefore the homework. All right, so if we want to prove this, then as usual, the first thing to say is let epsilon greater than 0 be given. Okay. And then the second part, where the real work is to analyze the quantity that we want to be small, namely our function f of x minus whatever the limit is supposed to be, L. You take that difference and you take the absolute value of that. That's what you want to be small. And in our case, this is equal to 1 over x minus 1 over c. And we want this ultimately to be less than epsilon. And the only thing that we're really allowed to control is how far away x is from c. Or put another way, we're allowed to control the absolute value of x minus c. Okay? All right. So, let me erase this. We'll start from that last line. So I guess tomorrow's April Fool's Day, and I've never been a big April Fool's guy, but the college I went to as an undergraduate the engineering faculty had a strong April Fool's tradition. And you have to remember two things. One, it's college in Canada, and in Canada, like the rest of the Western world, except for America, liability is not quite the thing it is here. You cannot sue somebody for $80 million for spilling a cup of coffee on you. It just doesn't work that way. Therefore, getting up to certain hijinks carries a lot less risk with it, legally speaking. And two, it was the 90s, you know. So, things were a little different. Anyhow, they would do all kinds of things on April 1st, and the two that stick out for me is that we had this physics lecture theater where the seating in the physics theater was in these sort of concentric rows like this, like a Wi-Fi symbol, and the chairs were just bolted on with a single bolt all the way along. And so at some point in the dead of night, they came in with a compressor and an air wrench, and they undid every single chair in the whole theater, and then bolted them back on backwards. And of course with an air wrench, so they were like impossible to get off unless they came back in and fixed it, which they did ultimately. The other one I enjoyed was that the other nice thing about a state university, well, they're all state universities in Canada, is that you actually have campus pubs. They don't treat you like a child. So there were a number of campus pubs, one for each of the faculties, engineering, arts, and science. And so the arts and science pub had this entrance that, if you're street level, it just had a set of stairs going down like this. And so what the engineers did for April Fools was they literally had a block of concrete cast that fit the stairwell, and they rented a whole crane and just lowered this block right into the stairwell so that there was no entrance anymore. It was just sidewalk where the entrance once was. Anyhow, those were the two big April Fool's jokes that I can remember. All right, so back to the matter at hand. So let's recall. So we want the limit as x approaches c of 1 over x to be equal to 1 over c. And here we're assuming, for the sake of simplicity, that c is greater than 0. This works just fine if c is less than 0 as well. It just makes the proof a little bit easier. Okay, and so what we have to consider, as I mentioned, is this difference. The function f of x, which is 1 over x, minus what we think the limit is, which is 1 over c. And you want to massage this thing algebraically so that the absolute value of x minus c appears in there somewhere, because that's the thing you can control. Okay? So maybe the first idea is to put everything over a common denominator, which will give us the absolute value of c minus x over cx, which we could rewrite as the absolute value of x minus c, all divided by, say, c times the absolute value of x. Okay? Or maybe, you know what, let me even rewrite this as, it's the same thing, I just want to separate those two pieces. Okay? So here then is the thing we can control, right? The absolute value of x minus c. We can declare that that's less than delta, where it's totally up to us what delta is. Okay? And, in general, if you have an expression like this, and if, for instance, this mess over here, this 1 over c times the absolute value of x, if that can be made less than or equal to some constant, then you're good, okay? Because then you just make x minus c less than epsilon divided by that constant, and the whole thing comes out to epsilon, and that's what you want. However, of course, this is not a constant right now. Right? This is not a constant, and I want you to think back to the example of the limit as x approaches c of the function x squared, right? In that case, we had the absolute value of x minus c, and then instead of this mess here, we had the absolute value of x plus c. And we had to do something. We had to make an initial guess at delta to get some kind of control over what the absolute value of x plus c was. Here we have to do the same thing, okay? And the idea is that we want to replace this thing with a constant, first of all, and we want to make sure that it's not too big. Okay? So what's the danger? The danger is that x gets very, very close to 0. Okay? C is a constant strictly bigger than 0, so if the absolute value of x gets close to 0, the denominator gets close to 0 and the whole thing blows up. Alright? So we want to keep x away from 0. So that's the first thing to do. We want a lower bound on the absolute value of x. Okay? So that's going to be what we use our first stab at delta for. Okay? So the thing I want you to keep in mind then is maybe a picture of the number line here. Here's 0. Here's c. I'm allowed to control the lighting. I'm allowed to control how far away x is from c. And I don't want x getting too close to 0. Right? So, let's make sure that x doesn't wander further away than, say, halfway to 0. And how far is that? Well, that distance then, of course, is c divided by 2. Okay? So that's our first stab at delta. We're going to say set delta 1 of epsilon to be equal to c over 2. And then we observe now if x minus c is less than delta 1 of epsilon, which is just c over 2, then we get a lower bound on the absolute value of x, right? So first of all, it will tell us that x has to be somewhere in the little neighborhood of width c over 2 around c, so x has definitely got to be positive, so you don't even really need these absolute value bars. But the other thing it tells you is that the absolute smallest this absolute value can be is c over 2. So this implies the absolute value of x is greater than c over 2. And that further implies, so if you have a lower bound for something in the denominator, that gives you an upper bound for the whole fraction, right? So that means that 1 over c times the absolute value of x is less than, I guess, 2 over c squared. Okay? And that's exactly the kind of result we wanted, right? We take an initial stab at delta. Here it is. Delta 1 of epsilon is equal to c over 2. And from that initial stab at delta, we can conclude that this thing here that we formerly had no control over, now we have some control over. It's strictly less than 2 over c squared, which is a constant. Good. All right, so let's summarize that on the next board. All right, so if absolute value of x minus c is strictly less than delta 1 of epsilon, which is equal to c over 2, then the thing that we're interested in, 1 over x minus 1 over c, absolute value, that's equal to absolute value of x minus c times 1 over c times absolute value of x, and that will be less than absolute value of x minus c times 2 over c squared. Okay? Now we're in business. By taking our initial stab at delta 1, we've been able to prove that the thing that we want to be small, the thing we want to be less than epsilon, is at least strictly less than a constant times the thing we can control. And so now all we have to do is make delta 2, make this thing less than epsilon over this constant here, and take our overall delta to be the minimum of delta 1 and delta 2. Okay? So, let's set delta 2 of epsilon to be equal to epsilon times c squared over 2, and set delta of epsilon equal to the minimum of delta 1 of epsilon and delta 2 of epsilon. Okay? And then if we call this star, we can say then star is strictly less than epsilon times c squared over 2. So that's just us replacing the absolute value of x minus c with delta 2 times 2 over c squared, which is, of course, just equal to epsilon. Okay? And that's what we needed. All right. So then part 3, we just tie all this up with a bow. So in part 3, we just say with delta of epsilon as above, if x minus c absolute value is bigger than 0 and less than delta of epsilon, then our f of x minus L absolute value, which in this case is 1 over x minus 1 over c, is going to be less than epsilon. Well, I guess if you really want to make it clear, you could say it's less than x minus c absolute value times 2 over c squared, which is then in turn less than epsilon times c squared over 2 times 2 over c squared, and everything cancels out. So, in conclusion, the limit as x approaches c of 1 over x is indeed equal to 1 over c. Okay? So it's another example of a problem where you need to take an initial stab at delta to find yourself a delta 1 of epsilon in order to get some control over some algebraic aspect of of this thing here, right? So you're going to substitute whatever your function is and whatever your limit L is, and you're going to wind up with something, some sort of algebraic mess, out of which you hope to get the thing you can control, here, right, times some other mess which you hope to make constant. And to make it constant, often you have to take an initial stab at delta. And this is the part where I would ask if you have any questions, and someone would earnestly raise their hand, and we'd have all that great sort of interaction, but we can't. It's depressing, I know. I got an alert on my phone this morning. This is great. So there's a tornado alert, you know? And all I could think is, like, I just wanted to call the tornado up and be like, you know, have you looked outside? You know? I mean, read the room, man. We got a pandemic going on. Nobody cares about you. What, are you going to rip up a few garden sheds? Do some property damage? Give me a break, tornado. Please. We have bigger fish to fry right now. Anyhow, so far no tornado, but I'm in the basement anyway, so hopefully I'll be good. And I was also reading this article that said, you know, I mean, if you're isolated and you're kind of bored, I mean, it's totally fine to talk to inanimate objects, you know, to anthropologize all the things in your house, right down to your, like, dishwashing liquid or whatever. But it's when they start talking back that you need to worry. That's when it's gone too far. That's when you need to go out for a walk or something. Yeah. Okay, so those are examples of limits, and the next thing, I'm of two minds about this. The book does this the other way around. I think it's pedagogically unsound, so let me ask this question. I think this is the next thing we should do. Question. What does it mean to say that the limit as x approaches c of f of x is not equal to L? Okay, so we've gone through the definition of what it means to be equal to L, but this is like asking, you know, what does it mean when something doesn't converge? And I guess the first thing I would point out is that we're not even commenting on whether or not this limit exists, right? This might exist and not be equal to L, or it might not exist at all. We just want to write down the logical statement that says that this is not the case, that the limit as x approaches c of f of x is definitely not equal to L. Whatever else it might be, it is not equal to L. Okay, so here's what it means. If you're keen on logic, what's going to happen here, just, I mean, this is a bit similar to what happened when we asked the same question for sequences, right? What does it mean for a sequence to not converge to a given number? And convergence always starts with for all epsilon greater than 0. And so its negation, its logical negation, starts with there exists an epsilon, we'll call it epsilon naught, greater than 0, such that, now formerly we had there exists a delta greater than 0, and now we're negating everything logically, so it should be such that for all delta greater than 0. And And before, it was the case that we had a statement that held whenever x, for all the x's that satisfied x minus c is less than delta. So for all delta greater than 0, now instead of all the x's with x minus c less than delta having to satisfy something, there just has to be one. Instead of for all, there exists, okay? So such that for all delta greater than 0, there exists an x with it's not equal to c, but its distance from c is at most delta. So it's getting really close to c. So there exists an x which is really close to c. Now this works for any delta. And yet, the distance from f of x to L remains greater than or equal to this epsilon naught, which is, of course, greater than 0. Okay. So, that's the logical string. What's really happening? Well, if the limit of f of x as x approaches c is not equal to L, it means that f of x has to stay away from L. Okay? So that's what this statement here is saying. Right? This is saying that f of x minus L is greater or equal to this epsilon naught, this fixed epsilon naught, which is in turn strictly greater than 0. Right? So that's saying that f of x stays away from L in a uniform way. And this other bit says, no matter how close you get, to C. Okay? So pick any tiny, tiny distance from C. It's still possible to find something that's that close to C for which you still have a problem. You still have that the distance from f of x to L is at least this fixed number, epsilon naught. Okay? So that's what it means for the limit as x approaches c to be not equal to L. And we're going to use that now to prove what is called the sequential criterion for limits of functions. And what this theorem is going to show is that the definition for the limit as x approaches c of a given function can be written down entirely in terms of limits of sequences. So that, in fact, in some sense, this new limit concept, it's not new at all. Once you know what a limit is for a sequence, then, in fact, you already know what it is for a function. Okay? So, and this, in fact, is where the notes for tomorrow, I guess, will be by the time I post this, April 1st, start. Okay? So, the sequential criterion for limits. Okay, so it's a theorem. So as usual, let f be a function with domain A and C a cluster point of A. Then the theorem says the following are equivalent. Right, so this is one of those abbreviations that appears over and over again. The following are equivalent. These next two statements are equivalent. One, is that you limit as x approaches c of f of x is equal to L. Okay? And 2 is where the sequences come in. It says for every sequence xn in A, so it should be a sequence of points from the domain with xn not equal to c and xn converging to c. Okay? So for every sequence in the domain which converges to the point, the cluster point C, and consists entirely of points different from C, we have that if you apply the function to that sequence, f of xn, that will converge as a sequence to L. Okay? So another way to think of it is, if this limit exists, then this function will carry convergent sequences to convergent sequences. I mean, provided you're talking about a sequence converging to the cluster point, C, roughly. Okay? This function, for sequences converging to C, will carry those convergent sequences to new sequences, f of xn, and those new sequences, f of xn, will in turn converge to L. Okay? All right. So, let's go about proving this. Proof. Let's start with part 1 implies part 2. Okay? So that means we assume part 1. So suppose the limit as x approaches c of f of x is equal to L. We want to prove part 2. Part 2 is a statement about sequences converging to C. Alright? So we want to let such a sequence be given, and we want to prove that f of that sequence then converges to L. Okay? So suppose that the limit as x approaches C of f of x is L, and that xn belongs to A, xn converges to C, and all the xn's are not equal to C. In other words, assume that we have one of those sequences from the statement of the theorem. Okay, and the idea is going to be this. This statement here tells us if you get really close to C, your function gets really close to L. Okay? Now these points here in the sequence xn, those are getting really close to C. And in fact, for a given degree of closeness, we could always give you a capital N, a natural number, such that for every element in the sequence whose index is bigger than that natural number, the distance between the sequential elements and C is then less than whatever tolerance you were given in the first place, okay? So, if you're close to C, f of x is close to L, and this statement here allows us to get close to C, okay? And the relationship between those two things comes from the definition of the limit of f of x equals L. So, if we would like to show that f of xn converges to L, then we need to start with epsilon. So let epsilon greater than 0 be given. Okay. Find, as we may, a delta of epsilon such that the distance from f of x to L is less than epsilon if the distance from x to c is less than delta of epsilon. Okay? So this is just basically restating the definition of what it means to have the limit as x approaches c of f of x be equal to L. Okay? Now what we're going to do is find a natural number, capital N of epsilon, big enough that the xn's, the distance from the xn's to c is less than this delta of epsilon, whence f of those xn's minus L will be less than epsilon. Okay? So find capital N of epsilon, a natural number, such that the distance from xn to c is less than delta of epsilon if little n is greater than capital N of epsilon. Okay? Now what's going to happen is whenever little n is bigger than capital N of epsilon, this statement here will be true, which means that f of xn minus L will be less than epsilon, and that's exactly what we need. Okay? That's the definition of f of xn converging to epsilon. So let me erase most of this, but not all of it. I'll even get rid of this. Okay, so it follows that the distance from f of xn to L is less than epsilon. And when does that happen? It happens exactly when little n, the index, is bigger than or equal to this capital N of epsilon. And that is the very definition of what it means for a sequence to converge. Right? You have then proved that f of xn converges to L. So that's one direction of the proof. That's one implies two. Okay. Now 2 implies 1. This brings up the reason why oh, come on. I never quite know what happens there. So, with 2 implies 1, now, this will bring up the reason why I wanted to introduce what it means for a limit to be not equal to L before introducing this theorem. In the textbook, they do that in the opposite order for reasons that are beyond the grasp of science. Or reason. Yeah. I actually I actually bothered to spend more than the absolute minimum on coffee at the grocery store today, given that I'm locked in the house. Normally I'm kind of a cheapskate about it. Boy, it really does make a difference. I mean, the other stuff just tastes like moose poop fried in motor oil, but this is good. For the most part, coffee is a functional drink for me. It's like taking medicine. I mean, it's necessary. But this is actually halfway to enjoyable. Oh, I gotta clean this basement. Damn. Anyway, yeah, and if you're wondering where all the, little barbell free weight plates are at Walmart, I bought them all. So don't bother. They get them in once a week, apparently. So, better luck next week. Okay, we want to prove 2 implies 1, right? We want to prove the statement that if it is the case that the function f carries sequences converging to C to sequences converging to L, then that is the same as the limit as x approaches C being equal to L. Okay? And what we're going to do, what turns out to be easiest, is to prove the contrapositive. I.e., not part 1 implies not part 2. Alright, so in words that would mean prove that if the limit as x approaches C of f of x is not equal to L, then it has to be the case that you can find a sequence converging to C such that the corresponding sequence f applied to that sequence, f of xn, does not converge to L. Okay? So let's write that down. Let's start again afresh. I don't even know if we're gonna get through this. Yeesh. Let me at least write down what we've got. So not 1. This is the same thing as the limit as x approaches C of f of x is not equal to L, which is the same thing as saying, as we pointed out before, there exists an epsilon naught greater than 0 such that for all delta greater than 0, there is x with the distance from x to C less than delta and bigger than 0, and yet the distance from f of x to L is greater or equal to this epsilon naught. Okay? That's the statement not part 1. And we want to use this to generate a sequence converging to C, which nevertheless has the property that f of that sequence does not converge to L. Okay? And so all we're going to do, in fact, is take this exact statement here, and we're just going to pick a sequence of deltas, right? Because this is supposed to work for all delta greater than 0, right? So choose delta n equal to 1 over n and find xn as above. So what do I mean by that? I mean, in this statement here, which is the logical statement that the limit as x approaches c of f of x is not equal to L, I want you to take, for your delta, the quantity 1 over n. Okay? And then, what the statement says is there's got to be some x, which then will be bigger than 0, such that x minus c, absolute value, is bigger than 0 and less than, well, now your delta is 1 over n, so less than 1 over n, such that this statement holds. Whatever that x happens to be, we're going to call it xn. Just pick one that works, call it xn. Okay, so then what do you have? Well, you have that your xn minus c is always going to be less than the corresponding delta n, which is 1 over n. In other words, the xn's are getting closer and closer to c. The distance from the xn's to c is going to 0, or the xn's are converging to c, okay? So then, xn is not equal to c. That comes from this inequality here. And xn converges to c, okay? So it is one of these sequences that appears in the statement of this sequential criterion for limits. It's one of those sequences, but f of xn does not converge to L. Why does it not converge to L? Because this statement is also going to hold for your xn's. F of xn minus L, the absolute value of that, is going to be greater than or equal to this epsilon naught. Achoo! Oh, coronavirus everywhere. Oh my god. So cut down on visitors for the next 14 days. Unless I really don't like them. Anyway, so then we've got this absolute value of f of x minus L greater than or equal to epsilon naught, and that's exactly the statement that f of xn does not converge to L. Okay? Alright, so that's the contrapositive. That's the statement not 1 implies, well, this part here is not 2. Yeah, and for the record, joking aside, I mean, it is an extremely bad idea to make any kind of wisecrack. I know it's April Fool's tomorrow. Take it from me, I'm kind of a news junkie. And I mean, absolutely no coronavirus joke whatsoever is funny. None of it is funny right now. Trust me. Okay? There was somebody in Missouri who, I believe, made some joke about he sneezed on a cashier and then made some crack about, the virus, etc. and was actually charged with domestic terrorism. Okay, so that's a very, very serious charge. That is not the kind of thing that your corner store county lawyer can make go away. Alright, so be careful out there, just stick to like replacing chalk with a tube of toothpaste or something like that. Alright, stay safe, wash your hands, and I will see you in a couple of days. And if you have any further questions, of course, feel free to ask them via email or Piazza. Oh, rats! Okay, let me quickly... Jeepers. So the question I had... Now we're going overtime. This is office hour now. So the question I had, briefly, was a question on the homework, and it's one of the questions that has a solution in the back, So I won't be specific, but ultimately, I think you're faced with something like this. You want that to be less than epsilon, okay? And here, x is approaching 2, okay? In other words, this is the thing you can control, and then here's this other thing that might be a nuisance, okay? If you look at the solution in the textbook, they take one of these initial stabs at a delta 1, and the delta 1 they choose is 1/2. It's not so important that they choose 1/2 exactly. What is important is that they choose a number that's strictly less than 1, because the thing you are worried about is this x getting really, really close to 1. Sorry, this whole thing getting close to 0, rather. Okay? So you want to keep x away from 1. If x gets close to 1, this denominator gets close to 0, and this thing explodes. So keep x away from 1. And that's why they choose an initial delta of 1/2 there. If you choose an initial delta of 1, you're going to have problems, because that will allow x to get as close as you want to the number 1, and then you will not be able to get an upper bound on this thing here. Okay, so this is somehow in the same sort of spirit as the proof of the statement that the limit of 1 over x is equal to 1 over c as x approaches c, where c is greater than 0. Okay, now we're done for real. And again, yeah, of course, if you have questions, feel free to ask them through email, Piazza, what have you. Okay, take care. Bye-bye.